thank you so much for joining us today. We have a very special guest speaker with us. Dr. Saquib Sarfraz is a deep learning lead at Mercedes-Benz in Autonomous System Unit and a senior scientist and lecturer at Karlsruhe Institute of Technology, KIT. He has a he has a va- va- he has a vast experience in deep learning and computer vision, and his research interests include deep learning, image and video understanding. This talk will be about large-scale data understanding in NLP and vision systems, and the title is Efficient Clustering and Visualization with Finch and h-NNE. So thank you so much, Dr. Saquib, for your time and overview.
Yes, thanks, Ahmed, for introducing again. Yes, as you have heard, talk is about efficient clustering and visualization, particularly with these two algorithms, Finch and h-NNE, which is topic of today. But before I go into it, I will very quickly just tell you more about my organization. So I'm currently a deep learning tech lead in an internal tech hub of Mercedes-Benz called Mercedes-Benz Tech Innovation. So for the past 25 years, it's the largest tech hub, 100% internal for Mercedes-Benz in Germany, and mostly focusing on IT and machine learning, data science topics within the whole value chain of vehicle manufacturing. And of course, I am here at the Technologies and Security in the Autonomous Systems, where we are particularly focusing on deep learning and AI and scaling out also currently generative AI technologies throughout the Mercedes-Benz. All right, so with this short intro, what we have today, basically, I just want to give you a kind of walkthrough with, we recently published, and not that recent though, but we did some work previously on clustering and data visualization. In particular, I would like to talk about the Finch clustering method. It was published back in 2019, but since then it has received quite well attention, I would say. And we have seen its uses in many, many use cases, not just in industry, but also in academic publications as well. So I would just give you a quick recap on Finch. And then we'll go a little bit more deeper into the how we can use this kind of clustering view to embed data, high dimensional data onto 2 or 3 dimensions. So that algorithm basically is called hierarchical nearest neighbor graph embedding. So these are the 2 main topics today. But just as a starter, in general, clustering and reducing dimensionality of high-dimensional large data is quite important in almost, I think, all areas of sciences. And for this purpose, clustering or dimension reduction techniques are quite increasingly used now. Main challenges are that they have to cope with an ever-increasing size of real-world data sets, and of course, it is kind of crucial because you anyways need it both for visualization, but also processing of high-dimensional data, right? So with this, I would just come to the main subject, which is first part is clustering. So what is clustering? I mean, we want to automatically discover some groupings in the data, right? And we kind of do it in our everyday work with everyday data sets. And mostly what we use for this task are quite common, well-known clustering algorithms, but those algorithms usually also have some limitations. And among those limitations, I think the largest or the biggest limitation is that you need to specify specific hyperparameters, like how many clusters you need, or other hyperparameters of distance thresholds, or in other words, you do need some kind of prior knowledge about your data before you deploy a specific clustering algorithm there. And to make things even more difficult, in many cases, these clustering algorithms, they do not really generalize quite well across different data domains or different high dimensional feature spaces, meaning that when you switch your data distribution, you need to then reconfigure or re-specify some other hyperparameters that would work well now for this data. So alongside, apart from the very famous k-means, most of the other recent clustering algorithms, or especially graph-based algorithms that we know, they cannot really scale to very large data because they would require prohibitive compute resources. I mean, largely because their memory requirements or their compute requirements are quadratic in that sense. So if you, for example, try using agglomerative clustering, hierarchical agglomerative clustering on millions of samples, you would find out that it's simply not possible to do it on a normal compute machine that easily. So here, basically, the idea is to the idea of this clustering algorithm, which we called first integer nearest neighbor clustering hierarchy, or Finch, it was to come up with, or try to come up with, some efficient and fully parameter-free algorithm so as to address some of the limitations I just was describing. So mainly, I think it would be really great if we do not have to specify hyperparameters like the required number of clusters, because in practical scenarios, when you do not have labels on your data sets, you do not really know how many clusters there are in your data, right? So it's basically would be really great if you could get some way of finding meaningful clusters without specifying this kind of limiting requirements or imposing these kind of requirements on the algorithm. So this Finch is kind of also quite compute efficient. It's with the complexity of n log n, and its memory similarly requires of n, which makes it really fast. For example, if we cluster 8 million samples, k-mean would take 56 minutes on a single machine, whereas Finch was able to do it in about 18 minutes, which is kind of a good yardstick to see that in these kind of realistic scenario, the time advantage for Finch is quite high. So next, I would give you a very quick walkthrough of how this Finch basically works. And the idea is basically based on an important observation that the very first neighbor of each sample in each data sample can form large linking chains in the data. And this observation is captured in this shown clustering equation, which specifies mainly two conditions to form the adjacency link matrix. And here, for instance, this symbol ki1, it represents the first neighbor of point I or point j, and the link between point I and j would be 1 when either of these conditions are met, and it would be 0 otherwise. So we'll explain it a little bit better in the next slide, but since the first neighbor is, we can obtain the first neighbor of a sample in our data set by using approximate nearest neighbor methods. So we do not really need to keep all pairwise distances of the samples in the memory because we are not computing all distances, right? And which is something that almost all the existing clustering algorithms require. And that is the main reason why such algorithms would require then a lot of memory to store all the n square distance floats. And so here, with only the integer list of the first neighbor of the data samples, we can produce natural groupings of the data. And we do not require then any other threshold or hyperparameters here, right? Because in this equation, as you see, all it requires is the indices of the first neighbor of each sample, and it just links those samples together, and it forms an adjacency matrix directly there. So the clustering equation directly specifies this adjacency link matrix, and whose connected components then are the clusters, and no further analysis such as solving a graph partitioning or distance threshold are required there. So as simple as that, right? And just to understand it a little bit better how it functions, in the paper we describe this small walkthrough, and I find it often useful to walk through it because one can really see what's happening there, right? So to understand this, how the large clusters are formed actually, we can look at this small tractable example of clustering the planets in our solar system. So we can cluster the planets in their known measurement space, and those measurements are, for instance, provided in the NASA fact sheet. So there are 15 measurements for already, and those measurements are, for instance, diameter, density, or orbital period of these planets. So in this 15-dimensional space, the first neighbor of each planet is, according to a Euclidean distance, is depicted here in this table on the left. And with this information, we can now form a 9 by 9 adjacency matrix using the equation here, right? And you can see that where it is 1 clearly because of this linking just the first neighbor to each other. The first condition simply connects, its immediate neighbor. And then the second condition is based also on an important observation that not all samples are symmetric. For example, in this here, you can see that Earth is the first neighbor of Venus, but Venus is not the first neighbor of Earth, right? So such samples also, connecting such samples is also the reason for inducing large linking chains in the data. So the second condition basically enforces this symmetry and links such samples discovering chains in this way. And third condition is basically only for understanding purpose, but because this condition is already met when we connect the first neighbor. But just to show you some inner working, it basically is linking points together who share the same neighbor, right? Which are anyways linked when you link to the immediate neighbor. So here instead you can see that Earth and Moon are linked together because they have the same neighbor, Mars. So this way, this whole adjacency link matrix can be formed very quickly. And then, as you can see the directed graph of this adjacency matrix, this clustering equation has already discovered 3 clusters. How you can see that how 5 out of 9 samples are merged into one big cluster here. While the 2 symmetric pairs are forming their independent clusters in terms of these connected components, right? And interestingly, though, the astronomers also use the same grouping for these planets, which here we have discovered. So this short walkthrough would give you an idea how this clustering is working. But that's not the whole story, though, because the clustering equation that I described so far, it delivers a flat partition with some predetermined cluster, right? So those are the connected components of this adjacency matrix that we just saw. So applying it recursively will produce, further successive partitions of this. And this is very useful because it enables us to have a hierarchy of clusters and greatly aids in data analysis. So because the clustering equation makes large merges, applying it recursively naturally converges in only few steps, providing a small set of hierarchical partitions where each partition would have some number of clusters in them. And here applying recursively also means that at each step we need to merge clusters now, not the samples, right? So in the first step, we get some clusters, and then we need to, in the second step, we want to merge those clusters to form another level of hierarchy. And this can typically be done by finding the first neighbor of each cluster. Yeah, and we achieve this very simply by just using the cluster means for that. So in that sense, the compute is still in check because in the next level, we are working still on not on all the samples, but on reduced samples, which are less than n, if n were the total samples. So this is an important point, that how many recursions you would typically need to ingest all of the data and produce an hierarchy, right? And one can see this also. There are some theoretical reasoning behind it as well. For instance, because we are building this one nearest neighbor graphs, and they are quite small in size, which also make them well suited to construct a fine-grained hierarchy with several levels, right? And a simple rule of thumb here is that the number of points decreases on average by a factor of about 30% on every step, which can be extracted from this famous theorem from Epstein, Peterson, and Yao, which, assuming that at least locally, if the data and centroids on higher levels are uniformly distributed, then this holds true. And I mean, practically speaking, the validity of this assumption is hard to verify, though, but at least we have noticed that this rule holds for many or most observed data sets. So it basically comes down at a very astronomical rate and typically produces few partitions. So no matter how large your data is, which is very manageable to look at and to use in the data analysis then. Right. So here is an example where we tested Finch on data of different sizes and dimensions, from 1,000 samples to 8 million samples in 77 to 4,000, more than 4,000 dimensions. And then we compare this to different classic and state-of-the-art clustering methods in the paper. But here, main point is that on the left side, you can see that the algorithm basically converges while producing meaningful merges. The left plot is the convergence, showing the convergence. And as you can see at each step, Finch produces some partition of data for different data set, right? At each step, it produces a partition. And when we plot the number of step runs for the algorithm in several data, one can see that in very few steps, we get, or produce a hierarchy of partitions. An example, let's take the example of the smallest data size, which is 1,000 samples. Here, Finch delivers a total of 6 partition. As you can see, 1, 2, 3, 4, 5, it's a total of 6 partitions in 6 steps of the run. And from 1,000 samples, it comes down to 351 in the first step, or the first pass of the clustering equation, to the ground truth 8 clusters in step number 4. And on the right, you can see that how pure are those merges at each step. So you can see that the relatively straight lines on the top shows you that it relatively maintains high clustering accuracy, indicating that the clustering equation is delivering actually meaningful merges at each step. So you can see the purity here. Okay, so since, as I said, I think the main benefit of using Finch would be that because it operates on the integer list of first neighbor indices, therefore the scheme is extremely fast and very memory efficient. And you can see some compute timings of Finch, including everything here in this table, which is pretty nice. And in the paper at the time, we just considered 8 million, largest sample was 8 million data set. And you can see that in comparison to some other algorithms, most of them would not be able to work. They would be out of memory on the same machine because of their quadratic memory requirements. But typically, overall, the timing for the Finch were really good. I mean, this is the table from the paper. At the time, we had a MATLAB implementation, but since then it has been developed quite nicely. So you find it, on PyPy and Python as well, where timing is kind of the same. Okay, so as a recap quickly, so that this Finch clustering, it returns a hierarchy of partitions without requiring specifying parameters, thresholds, or users or number of clusters. It's quite fast and compute efficient. And of course, discovering this kind of hierarchical groupings is useful in quite large-scale applications, from reducing annotation efforts to self-supervised, unsupervised learning. And we also use it for temporal data segmentation. So uh, chunking the data, like in this case, video data. So there is a TW Finch variant of it as well. So, okay, now with this, I will provide now a brief overview. We'll go into the next dimensional reduction topic. So, that like clustering, um, data visualization is equally important. And most popular dimensional reduction visualization techniques such as t-SNE, UMAP are often used. You might all have already heard of them. So I will just provide a little bit of in-depth overview of our h-NNE algorithm in this space. Like Finch, because it is using Finch clustering tree to project, it kind of retains its speed, scalability, and simplicity directly. So it has faster runtimes and also have ability to expose the clustering structure of the data, which is particularly useful for visualization purposes. So I stole this slide from somebody, and now I don't remember which lecture I got it, but it kind of puts the point very nicely that, for instance, if you have this kind of data which clearly have require nonlinear separation, then the simple linear algorithms won't work there, right? So the challenge for any dimensional reduction algorithm is to to preserve the global and local properties of the original high-dim data distribution in the projected low-dimensional space, but also to reduce this kind of information loss there, right? And we know that in the principal component analysis is one linear, well-known classic thing to do dimension reduction. But since it is linear, it probably won't really project the data into the showing you the clear separation of different data that you have in the higher dimensional space. So for that reason, the nonlinear methods are quite more effective and state of the art. So t-distributed stochastic neighbor embedding, or t-SNE, is really popular for the past 20 years or more than 15 years. And it's because it is so popular and so much longer in use now that it's faster and optimized variants are here. I think one noteworthy faster optimized variant of t-SNE is FFT accelerated. Is FLT-SNE. So it can do it also faster now. And similarly, another, I think, very famous dimension reduction state-of-the-art algorithm currently is the UMAP, which stands for Uniform Manifold Approximation and Projection. And there are similar other variants, ISOMAP, BACMAP, and so on, which are doing this. So I just want to give you a very quick idea of all of these dimension reduction algorithm, what they basically are doing. So for all of the dimension reduction algorithm, I think the intuition behind is that if you are close to a neighbor in a high dimension space, you want to be close to it in the lower dimension space as well. And if you are far from it, then you should retain that property in the low dimension space. So in other words, you want to preserve the neighborhood relationships that are present in the higher dimensional space when you're projecting data in the low dimensional space, right? And to do that, most of these, actually almost all of these current state-of-the-art dimension reduction algorithms, they typically construct a k-nearest neighbor graph in the original higher dimensional space. And where k is a user-specified parameter. Typically, it is 5 or 10 or 15. It depends. You can change it, and then it will change the visualization of your data. And the idea is to build this k-nearest neighbor graph first, so that you can get some local neighborhood distances of around each point in the data, and then you define weights between neighboring points by a function applied to a similarity metric. And then the distance, measured distance between points in high dimensional space then are used to, optimize an objective directly in the low dimensional initialized space, where we basically typically with gradient descent, SGD, you enforce that, okay, now you want to match the similar distance distribution of the high dimension points in this low embedded space. And this optimization objective is where basically is the main cause of the complexity, because it literally requires you to do this gradient descent on all of the points, matching in a typical contrastive learning way. So you compute some local close neighbors and some faraway pairs, and then you do the contrastive loss, typically both for t-SNE as well as UMAP. And the objective is to then push and pull. So you basically push the closer points together and pull the closer points together and push the farther points apart, right? So typical contrastive learning is then performed to finally obtain the embedding. Now, the advantages of these state-of-the-art techniques is that they typically try to preserve both global and local properties of the high-dimensional data, and they provides, in that sense, better embedding of the data with higher trustworthiness. And trustworthiness is a metric which basically measure if the neighborhood distances are preserved in a small 5 or 10 radius in the low dimension space or not. So in sklearn, you can read about it. They have implemented trustworthiness metric as well. Now, on the other hand, with these advantages in mind, there are some problems as well with these, these dimension reduction algorithms. I think the first one, or probably worthwhile to mention, is that it's not really easy to scale these to large data or millions of samples. I mean, if you have a low compute machine, typically UMAP or t-SNE basically won't scale out more than for millions of samples that easily. They require also larger memory and large compute machines to scale. And because they have expensive optimization process, this makes them slow. And I think the most crucial problem, which is their high dependence on the crucial hyperparameters. So all of these methods, if some of you already have worked with t-SNE or UMAP, you would notice that you have to define these typically perplexity or mean distance or these kind of parameters, which you need to change then to find different visualization for different data at hand, right? So this makes it a little bit problematic sometimes. And because of all of these reasons, they typically have slower runtimes. So our idea is to address again the problems of these techniques, was first of all to have something that can scale to large data easily, and to avoid basically the optimization step in these algorithms. So in this h-NNE, basically we are doing an optimization free projection. So we are not doing gradient descent or contrastive objective there. And there are no hyperparameters, mainly because we are not building k nearest neighbor graph, but we are just building a one nearest neighbor graph like Finch, right? So there we don't have to set the number k or any other distance threshold in that sense. And because of these reasons, it has a considerably faster runtime. Actually, in many cases, you can observe more than 5 to 20 times speed up, while it keeps mostly the advantages of the existing techniques, like it preserves the global and local properties of the data, provides the good embedding, and also higher trustworthiness. As you can see here, a small comparison on 1 million ImageNet data set, the whole ImageNet data set here. You can see that with various method, the trustworthiness score is acceptable. It's like not that bad. Actually, it's better than UMAP or PACMAP. With this optimized t-SNE, it's still very close. But I think you can see that the speed up is really noticeable, and it basically projects 1 million data points in 5 minutes, but in comparison to about more than 30 or 40 minutes for other methods. Faster runtimes, we actually measured this on many data sets in the paper, and in this table you can see different data sizes and different dimensions that in comparison to the UMAP or t-SNE variants, the running time is quite quite fast. 8 million samples or 11 million samples in about 12-20 minutes versus 3 to 5 hours for other UMAP or t-SNE variants. By the way, if you have some questions or you want to stop me and ask something, you can, of course, interrupt me anytime because it's a small round. I don't think so that we have to wait till the end of the talk, right? So please feel free to interrupt if you like. Now, I just want to give you some intuitive understanding of how basically it works, right? So basically, we want to build a one nearest neighbor graph, just like Finch, right? And use it to embed points such that it follows this build tree structure at each level of the obtained clustering hierarchy. And to do that, let's say we have a data X, which is a set of samples, n samples, and our first step is to construct this one nearest neighbor graph, which is the directed graph that connects each point to its nearest neighbor. So it's basically the Finch step, and this can be obtained, as I said earlier as well, very efficiently by using any proximate nearest neighbor algorithm. And then the next step is to identify the connected components of the graph, which would form directed graphs with all edges pointing to a single byroute, right? And like you see here, a small set of nearest neighbor graphs. And the third then point is then for each of these graphs, directed graphs, we compute the centroid and then form new set of points, right? Like here. So, and then we basically repeat the same process of computing the nearest neighbor graph on these centroids and its connected components to drive the next level of hierarchy. And we keep doing it until we reach the smallest set of centroids, typically which contain at least 3 points. So that's the top level of the clustering tree. And this one nearest neighbor graph hierarchy is then the clustering tree, where each centroid is connected to each of the points of the nearest neighbor graph component, which corresponds to it. So also, I think I also explained a little bit earlier that in contrast to methods that build k nearest neighbor graph, where k is typically more than one nearest neighbor graphs are quite small in size, which makes them well suited to construct a fine-grained hierarchy with several levels. Now the next step here, so far we just built the clustering tree, right? This hierarchical tree, basically the Finch, right? But the next step here, and which is also the central part of this algorithm, is to move these points now in a low dim space such that they follow this tree in a way that the original one nearest neighbor relationships are preserved over all levels. And we can achieve this with a fast recursive top-down approach by moving the clusters of samples towards the centroids. For instance, starting at the top level with the least number of points and moving progressively downward to reach the bottom at the final level, right? So what we are doing here is just that We are directly moving the cluster of points in the low dim space without any other optimization in place. I can go through this point translation process because that's the main part of the algorithm of h-NNE. So basically, we start from the top level of tree, but before that, of course, we have a preliminary projection, which could be just randomly uniform points, or you can have a preliminary projection of your data with PCA. By the way, not much difference even if you use random uniform random points in 2 or 3 dimensions to start with. And then the first point is to start then at the top level of tree and consider its projected centroids. And these centroids basically form a Voronoi tessellation in the low dim space. And an ideal way to place the lower level projected centroids would be to select for each point or each centroid at level L, say at level L, the centroids of level 1 below, L minus 1, that those that corresponds to this, right? And then translate them so that they are centered around the current chosen centroid. And then we finally spread them to occupy the corresponding Voronoi cell that's depicted here in this figure. So here in this case, this data at the top level of seven clusters, so 7 centroids. And you can see these Voronoi cells of those. We start there, and then, we just project the level 1 below points around this centroid and translate them directly there. In order to perform this process, of course, in an efficient and easy to vectorize way, we are not finding Voronoi cells actually, because that's not really efficient, right? So what we do is that we choose to use the already known distances of each centroid to its nearest neighbor in that level, because those are readily available when we build that clustering tree already. And then we just scale the translated lower level centroids to a d-ball radius, of 1/3 of this distance. So the idea is that here, if you have these centroids, then the distance between the nearest, like let's say if we are considering this centroid here, where my cursor is, then its nearest first neighbor centroid is this. Then we want to make sure that when we translate the points, they don't cross and form nearest neighbor relationships with the other centroid, right? So ideally, it should be less than 1/2 of the separation of this distance. And so to make sure that it will stay separated, we use the 1/3 of the radius of the distance ball around the center. And this distance actually guarantees that the points, as I said, they belonging to the neighboring centroids will not form nearest neighbor relationship across centroids, and then they would preserve the separation encoded in the tree, right? And once the points of level L1 below, level L minus 1 are placed around the points of, say, level L, then we use them to translate the points of level L minus 2 around them, and so on. Same way as before. So this step then is repeated actually until we reach the level of the data itself to form the final projection. So in all of this process, I hope you could follow a little bit of it. Of course, you can read more details in piece on the paper as well. But in all of this process, we are simply directly translating and scaling points, trying to preserve the clustering tree and the nearest neighbors or the cluster relationships that are there directly without any optimization. So as a recap for this dimensional reduction, you can understand the difference between different dimensional reduction algorithms. PCA or SVD, they preserve linear structure. t-SNE preserves local neighborhood distribution. UMAP preserves local connectivity, and h-NNE preserves hierarchical clustering structures. An interesting observation is also here shown. So here I'm visualizing an industrial time series dataset for anomaly detection. right? And these red points are the anomalies. As you can see in PCA projection or t-SNE or UMAP, the anomalies are spread all around. Actually, when you visualize it, you see that this anomaly is spread all over the place, right? But a clustering view like in h-NNE actually provides you a better view, I would say, right? It clearly shows that most anomalies are, uh, are clustered quite separately. And so this data set is not that good. It is trivial data set for anomaly detection because anomalies are already separate in the original space. So this is just to give you some idea about, why a clustering view could give some kind of insights that you can't get from the other dimension reduction algorithms. All right. Another important aspect for h-NNE is that it is quite helpful in visualizing unlabeled large-scale data because it already provides the clustering and the labels. So you can actually use the clustering labels to visualize different clusters, different groupings in the data and analyze them, right? So here in this example, I think this is also from the paper, it's a 3 million Google News NLP data set. And you can see that we have some cluster at the top level, 12 cluster, and we can see different clusters of this data here. And same, we can also move to the up to the hierarchy and visualize this data at a 43 cluster level or at a 174 clusters level. And this is useful when we are sifting through data or when we are trying to understand, different properties of our data. So for instance, because we have this hierarchical embedded structure, we can zoom into any cluster and locate it and zoom into it, and then at the level below we can see further clustering. So and then this helps us navigate the data and actually see those clusters, and how they are being formed. So you can imagine in today's rush with all the large language model and retrieval augmented generation use cases where you have to embed your data and then you need to see whether your choice of chunks make sense or not, or how the sentences are being related to each other, or how your query is related to in this. You can navigate with this quite easily in that space. One more thing I'm coming almost towards the end of my talk right now, but one more important thing is that for most of the computer vision researchers like ourselves or machine learning researchers, we typically use these these dimension reduction algorithm for monitoring the quality of the embedding, right, when we are training our deep learning models. And of course, you can see that how your model is progressing, how your embeddings are getting better, and you can actually see, the disentanglement that is happening along the process. But this is, of course, common. You can see that with any other thing, right? Not necessarily h-NNE. But of course, when you don't have labels, when you're doing unsupervised learning, then h-NNE already gives you a way to visualize different groupings on those labels as well. One important thing here, which basically what I want to mention, was that in current prevalent dimension reduction methods like t-SNE and UMAP, because they have this internal optimization step, right, with a contrastive learning objective, this extra optimization sometimes does not deliver the true picture of your embeddings, because these t-SNE or UMAP methods, they are running their own optimization, and they would give you an optimized view of the embedding space. So it's not necessarily it is the right space of your high dimensional data because of this extra optimization step on top. So here, for example, a clustering view can reflect poor separation of classes in the original space, because let's say your embedding is bad, so it won't separate classes that easily, and that clustering errors could reflect, the poor separation of the classes of your original embedding. So when you are really monitoring the embedding, this could make a difference how you visualize it, right? Because it is a desired property that when we inspect the quality of the features generated for data sets, you want to be actually as close to as how they are really, right? Including showing us all kind of mixed embeddings or classification errors that are there. So just to reflect on this point, another example, a typical, we use typical sentence embeddings for our retrieval-augmented generation. So here you see there are 4 different colors, which reflects 4 different types of documents. And we have basically, we are just seeing which embedder we should use for these documents. So we basically chunk the data and then we use OpenAI embedder, some other, say Ember, GT, so different embedders. And just here you see a view with UMAP and h-NNE, right? And in UMAP, you would now see this optimization impact, so to speak, that all of these embedders are very different. Some are good, some are not. But in the UMAP projection, it kind of cluttered, similar chunks closer together. So it is forming same kind of cluttered clusters of this green, for example, green type of document embeddings, right? And in h-NNE, these documents are quite diverse. I mean, they are same type of documents, but chunks obviously are possibly relating to different topics within those documents, right? So in the h-NNE view for the different embeddings, you can see that kind of also shows you this intercluster variability which is present, right? Shows you these islands and clusters. And so you can think about going in one of the clusters, see what are the chunks, where yours is your query, and help you get better insights of your data for your pipeline. So, okay, I think it kind of just wanted to say this. This was my own observation, so wanted to share with you it. And overall, I guess, as a recap, Finch is parameter-free, fast, hierarchical clustering, and h-NNE is an optimization-free projection of that, which preserves hierarchical clustering structure. And both do not require you to set parameters or threshold and have quite some faster runtime. And both are available on PyPy, and there are several notebooks also to give you a feel of how how they work. You can try them out, and the respective papers are, of course, also you can find there on their GitHub repos. So that is it. With this, I would end this presentation, and I'd ask you also if you have more some questions or points, feel free to ask. Also, we are hiring, so if you are interested in machine learning, data science topics, you could also, consider contacting. All right. So with this, that's it. I think. Thank you very much for your patience.
Thank you very much for the great talk. We do have a few questions.
Sure.
You can unmute Cyril and ask the question. Okay, so I'll ask a question which I had. So for the Finch and the h-NNE, the current workflow is like, first we have to pass the image to a model from which we can get embedding, and then that embedding is passed to these algorithms for visualization, or does this work directly on the images?
I mean, you can visualize anything. You can visualize pixels as well, right? In many of the examples I was showing were actually, or in the paper, we just visualize directly pixels. So you just put the whole image as a vector. And of course, it's not going to show you much better. Embeddings are better to visualize, but you can visualize the data in its pixel space as well. All it needs is a
Right.
vectorized form of representation for your data. Those could just be the
Right. Right.
pixels.
Right. Got it.
All right. Yes, Rohan, please
Uh,
feel free to speak. Don't need to raise
yeah,
hand.
yeah. So, am I audible? Can you hear me?
Yes, we can hear you.
Yeah, okay, I don't really have a question, but I actually have a doubt because I learned something new today. And so I was just thinking, and it got me thinking. So, there is a concept called as image thumbnailing, right?
Mhm.
So, like the example you showed, you were directly kind of encoding pixels directly in order to get a better visualization. And as you rightly said, embeddings would give you a much prettier visualization for the same.
Mhm.
So, as a concept of, like the de-blurring images or a lot of use cases where a lot of object detection models take a certain size of input for processing. So, do you think like using such algorithms, we can come up with a way which can give us an understanding before pre-processing or anything like that? Because at the end of the day, it's going to be pixels.
In the case of images,
Yeah.
I mean, the thing is that pixels are, I mean, they would not give you much insights in the pixel space of your, especially for the object detection examples, right? Because in the pixel space, everything is really looks space similar. Maybe it can help you see the some impact of different colors or so on. But I don't think so that the visualizing the pixel space would give you much better understanding of how those images are. You do need some kind of semantic embedding on top to visualize the images to see what kind of semantic knowledge these images are carrying. And in nowadays, those embeddings are easy to get, right? You have so many pre-trained models. You can get the embedding from any of the pre-trained model for your images to visualize them. But
Uh,
I
okay.
mean, these algorithms are just clustering some data, no matter what data you have. If you want to see cluster your pixels, you can do it. You, I mean, it's like a tool, right?
Yeah,
But I think
understood.
pixel space is not gonna give you much better visualization of what is in those images.
Okay, understood. Yeah, thanks for explaining me and pointing me to a direction. That semantic embeddings, right? Yeah,
Yeah,
yeah, yeah. Thanks for that.
sure. All right. So I don't know, Ahmed. I think we don't have any more questions, right?
Yeah, I think
And we
we
are
can end the
almost
session here.
time on time as well. 2 minutes are left,
Yeah.
so great. Then, guys, I would like really suggest to at least go through these their GitHub repo. There are several notebooks, and it's really easy. In minutes, you can run it. Seriously, try it out yourself to see all these things I was talking about. You will find it very useful.
Thank you so much for the session.
Thanks. Thanks a lot, everyone, for joining in. And I wish you good evening. At least in my time zone, it's evening. If any of you have still morning, so then mm, I wish you a good day ahead. Bye
Take care,
bye.
everyone. Bye.
Thank you very much.
Yeah,
Bye.
thank you.